This last session of the school, and it's really a pleasure to welcome today Nicola Spaldin. She's a professor of materials theory in the Department of Materials at the ETH Zurich. She studied in Cambridge. She got a PhD in Berkeley. She's been a member of the faculty at UC Santa Barbara for quite some time. I think this is where actually we met for the first time. She was actually directing at the time this beautiful international center for materials research. And then she moved to Zurich in 2011. She got several prizes. I'm not going to the list of prizes. I mean, been quite successful. Nicola, but just me mention one. I mean, one is quite, important, which is the L'Oréal UNESCO Award for Women in Science. This is the top award for women scientists. But this is also allow me to mention that Nicola's been strongly advocating for gender balance in basic sciences, and really thankful to Nicola for the support here at the ICDP. So the title is quite interesting. It's finding happiness and saving the world through electronic structure calculations. And I guess I'll stop here and let you go ahead, Nicola. Thank you very much again.
Thank you, Sandro, for the kind introduction. And it's a pleasure to be joining the school. It would, of course, be much more of a pleasure to be getting to meet you all in Trieste, but this is the best that we can do at the moment. So yeah, the title of my talk is how we can use what you've been learning the last couple of weeks to save the world and also hopefully find happiness. And I'm going to start by flashing up a slide that probably most of you are very familiar with, the United Nations Sustainable Development Goals. And I'd like to make the case that none of these goals are reachable without advances in science and technology, in particular material science, and the kinds of electronic structure calculations that you've been learning how to do in the next couple of weeks are really essential in contributing to meeting many of these goals. So if you get a little bit tired, I know it's been a long couple of weeks for you in the next hour, have a think about what you're doing in your research or your research direction, your research goals, and how you see that contributing to helping meet some of these sustainable development goals. I'm going to give you a couple of examples of my research, some of which we kind of aimed to achieve and others which were really quite by accident to give you some ideas, hopefully. Okay, but first we have to learn some stuff because, of course, saving the world is not easy. And so I want us to learn a little bit more electronic structure theory if you didn't feel like you had enough in the last 2 weeks. And I want to focus on a breakthrough which happened actually partially in Trieste in the 1990s. And that was the development of what we know as the modern theory of polarization, which if I understand correctly, you haven't really touched on. Some of you are probably a little bit familiar with it, but you didn't really study it in detail in the school. So I'll give you a little bit of background, and then we'll go and see how we can use this to try and find happiness and save the world. So the two papers I'm referring to by Raphael Aresta and Kingsmith and Vanderbilt really introduce the formalism for calculating electric polarization in crystalline solids. And let's take some time to think about why that was a really difficult thing that they did and why it was such a huge breakthrough. It's such a huge achievement that they were able to do it. The question that they answered was, is the polarization of a periodic solid a bulk quantity? At the time, it was still believed that it was perhaps a surface quantity. It wasn't so clear whether it was a bulk or a surface quantity. And if so, how should it be defined? And this is not a problem if you have a finite system. If you think about just a molecule, say with a negative charge of -1 electron and a positively charged ion +1 electron, then we can trivially write down the dipole by just summing up the sizes of the charges times their position, and we get a dipole of E, it's the size of the electronic charge, times D, the spacing between the ions, and the dipole is pointing from negative to positive. So there's no ambiguity. If we're interested in molecules or finite sized systems, we can write down the dipole. The problem is when we have a bulk periodic solid, and you can think, well, okay, that can't be so hard. Why don't I just write down the dipole moment per unit volume? That could be a good description of the polarization. So let's try that. Let's imagine we have a bulk periodic solid, just a one-dimensional chain made up of polar molecules. And we write down the dipole moment of this unit cell in the middle and divide it by the volume of the unit cell. And we get a polarization, which makes sense. It's the size of the dipole that we had previously divided by the volume. Because we have a bulk periodic solid, though, we can choose anything we like for the unit cell, right? We don't have to choose the light gray lines that I've drawn here. We could make, say, this choice for the unit cell. And if we do that, and we now work out the dipole per unit volume, we work out the dipole by summing over the charges times the position again, then we get a different answer. We get E times D over V, like we did before, minus E times A over V, where A is the size of the unit cell. You can give that a go yourselves, just make this your unit cell and sum over the charges times their position, times their distance from the origin, and you'll find you get a different answer. So there's two problems here. One is that we have a different number for the polarization if we define it as dipole per unit volume. And it's also pointing in the other direction, right? Our polarization points from negative to positive, and now it's pointing to the left in the unit cell. So this was the problem that this breakthrough of Rester and Kingsmith and Vanderbilt solved. I want to point out just one thing, that this difference here between the value we got for this unit cell and the value we get for the bottom unit cell, it's the electronic charge times the lattice vector times the size of the unit cell divided by the volume. And this is going to pop up again and again and again, repeatedly. We call it the polarization quantum. It's like a unit, a kind of chunk of polarization, the polarization quantum. Okay, so this is a nuisance. We don't have a simple way to define polarization for a periodic solid. It gets worse, actually. The problem is even worse than it seems already. And we can see that if we look at a centrosymmetric lattice. So now I've made, again, the simplest possible periodic solid I could make of just alternating negative and positive charges. And this time they're all spaced a distance d. So this system is not polar. It doesn't have a dipole, because if I sit on the positive charge, the negative charge is equally far apart to each side. So there's no, it's centrosymmetric, has the center of inversion. It's not a polar lattice. It doesn't have a net dipole. And let's do the same, repeat the same process and just work out the dipole moment per unit volume. And I'll start by choosing this unit cell. And if I sum over the charges times their position in this unit cell, I get minus E times D over V. If I take this unit cell on the left here, I get plus E times D over V. And I could keep going. I could construct all kinds of unit cells that might look a bit weird, maybe say containing this cation together with this anion, and I'd get very many values, which would all be E times D over V plus some integer times E times A over V, this polarization quantum, the electronic charge times the lattice vector divided by the unit cell volume. Or I could rewrite that. I could write all of the numbers that I can generate for the dipole moment per unit volume of this centrosymmetric lattice in terms of the polarization quantum. And what I see is I get PQ over 2, 3PQ over 2, 5PQ over 2, and so on. These numbers are all separated by the polarization quantum. But my numbers don't contain 0, even though it's very clear that this is a non-polar lattice, and by any sensible definition, I'd want to say its polarization is 0. What you can see is that this array of numbers that I have is a centrosymmetric array, right? We call this the polarization lattice, and it is centrosymmetric, but it doesn't contain 0. So these were the problems. This was the status in the early 90s that needed fixing. And this modern theory of polarization that was introduced solved this problem. And there are 3 key results. Let's look at 2 of them first. The first result was that the polarization of a periodic insulating solid is really a bulk property, but it's a multi-valued property. So polarization is not a single number, it's an array, it's a lattice of numbers, and it's given by some P0 plus n times the polarization quantum. where the polarization quantum is the charge times the lattice vector divided by the volume. Centrosymmetric solids, those that are non-polar, have centrosymmetric polarization lattices. And if you make any array of numbers, if you want the list of numbers to be centrosymmetric, to be equal at the plus or minus, there are only two ways you can do that. You can do that if they contain 0, or you can do it if they contain a half a quantum. And so these, I'd say, are two really key results of the modern theory of polarization. Okay, so this might seem a little bit unsatisfactory though, polarization. We like to think, okay, it's just like, should be a number, it should be a kind of thermodynamic quantity, and how can it be this list of numbers? And let me show you how we connect this slightly abstract behavior to experimental reality. And to do that, we should compare our centrosymmetric, our paraelectric, our non-polar lattice, so this alternating plus and minus ions, with the ferroelectric polar case that we looked at first. And I've tried to line these up so that I've lined up the anions, the negative charged ions above each other. And in the ferroelectric polar case, I've just shifted the cation to the left. So the dipole is made by, each cation is, sorry, to the right. Each cation is shifted to the right to make the polar case. And if we compare these two, if we look how the polarization, how the dipole moment per unit volume changes between the centrosymmetric paraelectric and the polar ferroelectric structure, if we choose this unit cell, we see that the dipole has changed by a charge of +1 shifting to the right by delta. If we choose this unit cell, which started off with a different value for its dipole moment, again, the change in polarization as we've gone from centrosymmetric to polar is a charge of +1 shifting to the right by a distance delta. So whichever unit cell we choose, whichever branch of the polarization lattice we're sitting on, whichever value we're taking of this many valued quantity, we get the same answer for our changes in polarization. The change in polarization is plus the electronic charge times the distance the cation is displaced divided by V. And of course, when we make a measurement actually of ferroelectric polarization, what we measure is always a change in polarization. We, for example, switch the orientation of the electric polarization and see how much current flows through an external circuit when we switch it. So we have an exact connection between the theoretical situation and the experimental reality. Okay, so I'm adding that to my list of key results of the modern theory of polarization. Polarization is multi-valued. Centrosymmetric solids don't have to contain 0 in their list of possible values. And this is all okay because differences in polarization, for example, the spontaneous polarization, which is the change in polarization between a paraelectric and a ferroelectric state, are single valued. And that is all that we can measure experimentally. Okay, I'm not going to go through too much of like the actual background theory that the kind of proofs that underlie these statements. You should either go back to the original papers if you're really comfortable mathematically. If you want a kind of easy conceptual introduction before that, I have a kind of, not really a tutorial article, I guess, which is a little bit more gentle introduction. And I also have a series of YouTube videos if you don't want to read, if you just want to watch the movie, which will give you a little bit more background. I thought I should, before we go on to use this though, I should just tell you practically how, if you want to calculate a polarization using quantum espresso or any other electronic structure code, how should you go about doing it so that you have that kind of, in your toolbox, you can go practice with the skills you've been learning the last couple of weeks. So the first thing, if you have a bulk periodic solid and you want to calculate its polarization, first is you have to calculate the structure of the solid. You have to calculate the positions of the ions. And what's super important is you have to make sure your system is insulating. If something is metallic, it can't sustain an electric polarization. And so I'm sure you've been learning this week about, for example, magnetic insulators. These could be rather challenging. to achieve insulating behavior in a density functional calculation. So you have to be very careful and make sure that your system is insulating in order to have a sensible definition of polarization. Once you have that, then you have a few choices. The first option is you can do just what we've been doing with these cartoons. You can take all of the ionic positions and multiply the position of the ion by the formal charge and add them up. So you can work out the dipole moment per unit volume just by simply saying, okay, calcium is +2, oxygen is -2, lithium +1, and so on. Sum over those formal charges and multiply by the positions. This is an approximation. It doesn't give you really the true answer, but it actually is not bad. It's not a bad approach. It's not going to be too far off from the true answer. If you want to get formally the correct answer, you can do one of two options. The first option, you would first sum over the ionic positions again and multiply by the pseudo charges, the charges on the pseudo potentials. And that gives you the polarization, the dipole moment per unit cell coming from the ions described by the pseudo potentials. Then, of course, you have to add to this the contribution from your valence electrons, and you can calculate that by summing over the centers of the Vanier functions, the Vanier centers, multiplied by however many electrons each Vanier function takes, usually 2 or maybe 1 if it's a magnetic system. And this approach is formally correct. This gives you formally the correct DFT value for the polarization. I'm not sure if you learned how to construct Vanier functions in the last couple of weeks, but this is a very nice kind of capability or extension to quantum espresso. Quantum espresso is one of the codes that's most set up for calculating these Vanier functions. The third option, which is also formally correct and is formally identical to option 2, is to sum over the ionic positions multiplied by their pseudo charges. That gives you the ionic contribution again. And then to get the part coming from the electrons, you can make what's called a Berry phase calculation of the electronic contribution. This is basically the same as the Vanier function contribution, but working in reciprocal space instead of real space. And some codes are more structured to make the Berry phase calculation more convenient than the Vanier construction. So you can take any of these methods, but what you have to realize is whatever option you take, your answer will be multi-valued. You will never get just one answer. You'll always get the answer plus n times this polarization quantum. And that you can't get around. It's not wrong. That's really the way bulk polarization in a periodic solid exists. Okay, so that's the end of the difficult bit, the stuff you have to learn if you want to save the world. And now I'm going to talk about some examples. I suggested to Sandra at the start, if anyone has questions that you really need clarifying, just type them in the chat and he'll take a look. And if everybody types in, I have no idea what she's talking about, I can go back and explain some stuff again, or otherwise we can take questions at the end too if you prefer. So just go ahead if you type in the chat if there's something you'd really like to ask right away. Okay, so let's look and see how this works in a real material. And the material that I've chosen is a perovskite structure oxide, bismuth ferrite. It's what's called a multiferroic material. And that means that it's both ferroelectric, so it has a spontaneous polarization, which is along the diagonal of the perovskite unit cell. And it's also magnetic because of the presence of the ion. So the ions have a very large magnetic dipole moment. They're surrounded by an octahedron of oxygen ions in the perovskite unit cell. And the ions, of course, provide the magnetism. And then the bismuth ions that are at the corners of the unit cell in purple here, they provide this very large electric dipole moment in the unit cell. Here's a picture of one of the earliest known crystals of bismuth ferrite. This is a rather beautiful sample. It's a single crystal, this kind of fern-like structure. These are twins. These are different orientations of the polarization kind of meeting each other, and that gives it this rather beautiful texture. So this is a sample from the 1980s from the late Hans Schmidt from the University of Geneva. You can see, we mentioned already that ferroelectrics have to be good insulators. This looks like a metal. It's actually not a metal, it's an insulator, but it has rather a lot of defects in it. And so this is why it has this kind of kind of black color. So it's a very pretty crystal, but not a particularly good crystal for doing high quality characterization. And it certainly can't be, you couldn't switch the polarization electrically. So it's not good for making ferroelectric devices, for example. Here's another sample. This is a sample from the early 2000s from the group of Ramesh, and this is a high resolution electron micrograph of the same material, which you can see is very perfect, at least over the length scale of a few nanometers. So this is this high resolution electron microscopy method is looking down columns of atoms in the structure. So it would be kind of looking down this direction in the cartoon here. And the white dots are columns of bismuth atoms. So you can see it's forming the kind of cubic perovskite structure. And maybe you can see, if you have a good screen, these very slightly lighter dots in the middle. These are the iron ions. One doesn't see the oxygens with this technique. And if you have very good eyesight, you'll see that the iron ions are not exactly in the middle of the bismuth ions. And that's because there's a structural distortion in the material that makes the dipole moment. Of course, it would be easier to see the dipole if we saw also the oxygen anions. So this was a real breakthrough for the field of understanding ferroelectricity and these magnetic ferroelectrics when such beautiful high quality films could be made. Yeah, and so the polarization is along the 111 direction. This film is grown so that 111 would be in the diagonal. And so the polarization, this is a kind of a thin film, a layer, the polarization that's pointing out of the plane of the film, which is the part that can be measured, has a value of about 50 microcoulombs per square centimeter. And we'll come back to that number later. You don't have to remember it. Okay, so I want to show you then the first calculation of the polarization in bismuth ferrite, a density functional calculation of the polarization, to illustrate some of these concepts that we introduced at the start of the talk. And so this is work done in 2005 by Jeff Neaton, Claude Ederer, Umesh Vagmare, myself, and Karen Ray. And what's being plotted here is the polarization. I converted it to the polarization in that 001 direction, perpendicular to the plane of the film, because that's what I want to discuss later. And the x-axis here is the percentage of distortion, where 0 represents the centrosymmetric paraelectric structure, so with no polarization, and then plus R3C is just the space group of the ground state, plus 100 means the system is completely relaxed to its ground state with the polarization in one direction, and minus 100 is with the polarization reversed in the opposite direction. So the ferroelectric polarization switch. Okay, so I want to point out a couple of things. And first I want us to look at the undistorted, centrosymmetric, non-polar structure and look at the values that one calculates for the polarization. I have to confess, I think this was done using the VASP code. I'm sorry, it was a long time ago, I don't remember. Oops. But let's look at the values. And for the unpolar, non-distorted structure, we see that we don't have 0 as a polarization. We have 50, minus 50, 150, minus 150, and so on. So this is exactly or analogous to the simple one-dimensional chain that we looked at. The undistorted centrosymmetric structure has a polarization lattice that doesn't contain 0. It contains instead the half polarization quantum, which turns out to be 50 microcoulombs per square centimeter in this case. Okay. Then when we gradually allow the structure to distort to its ferroelectric structure, you see that the polarization evolves from the value in the undistorted structure. And whichever branch on this polarization lattice we choose to evolve from, whichever unit cell, if you like, we pick to evaluate the polarization, we have exactly the same evolution. And the measurable bit that we measure if we do a switching experiment, what we call the spontaneous ferroelectric polarization, that's the difference between the ferroelectric and paraelectric values. That's the same in every case, right? And so whichever of these branches we measure or we calculate along, we get the same value for the spontaneous polarization. Here's the polarization quantum. This is the charge times the lattice vector divided by the unit cell volume. And in this case, it's about 100 in these units, microcoulombs per square centimeter. Okay, so that's how it looks when you go and make a density functional calculation of polarization for a bulk periodic solid. Okay, a couple of things I want you to notice. The first is this 0 here, and also over here. Oops. And this is an allowed value for the polarization of the fully ferroelectric structure, if it's in one orientation or another. The allowed values of the polarization are 100, 200, and so on. The spontaneous polarization is 100 minus 50, it's about 50 microcoulombs per square centimeter. But one of the allowed values is 0. And this is not something we noticed at the time, but it's going to be significant for some new results I want to show you later. Okay, so we have this 0 in our allowed values of polarization for the actual ferroelectric polar structure. The other thing I want to point out, and this might be totally familiar to many of you, is what the units are of polarization, because this is going to lead us into the next point. So the units, so remember polarization again is dipole per unit volume. Dipole is charge times distance over volume, which is distance cubed. So the units of polarization come out as charge divided by area, right? So charge times distance over distance cubed is just charge over area. And in the ferroelectrics community, for some reason, which I don't know why, that usually the charge is given in microcoulombs, so 10 to the minus 6 coulombs, and the area is given in centimeters squared. I guess because then you get kind of nice numbers coming out for your values. So microcoulombs per square centimeter. Okay. So that leads us immediately to see that associated with ferroelectricity, associated with the ferroelectric polarization, is a surface charge. Just by looking at the units, we can see that immediately. And this is really the case. Here's a kind of bulk solid. Again, it could be a thin film. It could continue in the direction in the plane. And the bulk polarization, the electric dipole per unit volume, is some value, let's say P, perpendicular to the surface, microcoulombs per square centimeter. When I make a top surface, then above this spontaneous polarization, I have then a surface charge of plus P microcoulombs per square centimeter. So the size of the surface charge is equal to the size of the bulk polarization. And likewise, if I make a surface at the bottom, when the polarization is pointing up, if I make a surface at the bottom, I have a polarization whose size is equal to I have a surface charge whose size is equal to the bulk polarization, but whose sign is now minus. I have minus P microcoulombs of charge on the bottom surface for every square centimeter of surface. Okay. And this is, one can see just from dimensional analysis. So this surface charge is very nice if you're, for example, interested in catalysis or electrochemistry, then you want to have a surface charge because it makes a surface reactive. If you want to have a stable ferroelectric device, let's say you want to store information in the direction of the polarization, having surface charge is very bad because you know that Gauss's theorem, this is electrostatically unstable. There's a diverging, there's a discontinuity in the electrostatic potential, a diverging electric field. And so, particularly when you have a very thin film, so that these surface charges can be large relative to the volume and very close together, then this can be very detrimental to the behavior of a ferroelectric. And so what can happen, it's usually bad news. People spend lifetimes trying to figure out how to compensate this surface charge. So it will somehow try to suppress the polarization. So for example, the polarization might go in plane, right? Because if I have a film and my polarization is in plane, then I don't have any surface charge on the surface. The polarization might split up into domains, because then I have only a little bit of positive charge here and then immediately some negative charge. So averaged over this whole surface, then I don't have any so much net charge. The system might spontaneously generate electron hole pairs to compensate the charge. So it might make excitations of electron hole pairs across the gap, so the electrons can come and sit on the positive surface and screen and kind of neutralize the surface charge. The holes can go to the bottom surface. And it can even make a phase transition even to a state that doesn't have any polarization. So it can go and stabilize the paraelectric state, or maybe even make a completely new phase that's actually non-polar. And I want to start by showing you an example of this last case, because it's a really beautiful example, I think, of where density functional theory calculations were able to contribute to understanding this topic. Okay, so this is work that was done by Giulia Mundi, who's now an assistant professor at Harvard University, and Bastian Grosso, who's a PhD student in my group, who did the density functional calculations. And here's another high resolution transmission electron micrograph of a film that Giulia grew, which was made of lanthanum ferrite. So lanthanum ferrite is not a ferroelectric, it's a non-polar material. Then bismuth ferrite, the material we've been discussing, and then lanthanum ferrite again. And we want to look at the layers in the bismuth ferrite. Remember when we looked at bismuth ferrite previously, we're seeing the bismuths again. When we looked at bismuth ferrite previously, the bismuths formed a nice kind of square array because they all shifted in the same direction to make the ferroelectric polarization. In this case, you see that Giulia's blown up a kind of section here. We have this pattern of two bismuths going up, then two bismuths going down. The blue circles are the ions. Then we have a row of bismuths not going anywhere, and then a row of bismuths where two go down directly below the two that went up before, and then two go up where the two went down before. And so Giulia came to us and said, well, what on earth's going on here? They had these microscopy images, but this kind of pattern of bismuth displacements did not correspond to any known phase of bismuth ferrite. And so Bastian was able to use density functional calculations to search for structures, for arrangements of the bismuth ions relative to the FeO6 octahedra in perovskite-based bismuth ferrite that were, of course, higher in energy than the ground state, but not too high in energy. And he was able to identify a new phase, which had not previously been considered, which is PNMA symmetry, and has this anti-ferroelectric pattern of the bismuth. As you don't see it so well from this orientation, but it's two up, two down, then a layer where they're all the same, and then two down, two up, and so on. And this was only 30 millielectron volts per formula unit above the R3C ground state, the usual ferroelectric ground state. And then he was also able to show, using a simple electrostatic model, that if your film is thin enough, so here he's plotting the energy in millielectron volts per formula unit as a function of atomic repeat units. So bismuth, a bismuth oxygen layer plus an iron O2 layer. For the R3C structure, which is ferroelectric and has this problem with the surface charges, and for his new structure, which is I'll show in a moment, is anti-ferroelectric, so it doesn't have any surface charge. And so the R3C structure, the ferroelectric structure, its energy goes up and up and up as it gets thinner because of the unfavorable electrostatics. But this non-polar structure doesn't care about getting thinner because it doesn't have any surface charge. And so below a certain thickness, it becomes the stable phase. It has what's called anti-ferroelectric hysteresis. Look at the blue lines here. So in the absence of any electric field, the polarization, the measured polarization is 0. But when you apply an electric field, it switches to a polar state. You take the field away, it switches back to this non-polar state, and again in the other direction. And these antiferroelectric materials are very important because they're candidates for very high energy storage. So this is my first example of a density functional theory calculation being used to engineer materials that might contribute to saving the world in terms of affordable energy and climate action, because one needs, of course, if one has an alternative source for energy, to have a way to store it, and antiferroelectrics are candidates for this. Okay, I wonder, are there any questions, Sandro? I see the number ticking up in the chat, but I can't see the questions. So if anybody wants to ask anything, I
don't see questions in the chat for the time being. I asked everybody to write their questions in the chat if they want to ask questions. So I'll keep monitoring that. Okay, I'll keep going then. I'll give you like 10 seconds to kind of breathe, because now I'm going to do a totally different example. Okay. Okay, so that was our first example, designing new anti-ferroelectric materials based on the understanding about polarization that we're able to gain from our electronic structure calculations. I want to introduce another concept now, and this is going to be the finding happiness part. So if you're waiting to see how your electronic structure calculations can make you happy. So I want to go back, remember, to this simple polarization lattice we had of just plus minus charges, the centrosymmetric lattice that was non-polar, but it didn't have zero as any of its allowed values. And bismuth iron oxide, in fact, is analogous to that very simple example that we looked at earlier in its centrosymmetric form. So when bismuth ferrite is in a non-polar paraelectric structure, for example, if it's in the ideal cubic perovskite structure, its polarization lattice doesn't contain zero, it contains the half quantum. Oh, sorry. Yeah, okay. And I can illustrate this here. Here's perovskite structure, bismuth ferrite, in its ideal cubic structure with no polarization. So the ion is right in the middle, the positive ion is right in the middle of the negative oxygens. The bismuths are exactly at the corners in a square, and so there's no dipole. If we look at the charges of each layer, this layer in the unit cell has 1 bismuth and 1 oxygen. It's bismuth 3 plus oxygen 2 minus, so it has a charge of plus the electronic charge. The next layer, 1 iron, and 2 oxygen ions. The ion is plus 3, each oxygen is minus 2. So the charge in this layer is minus 1 electronic charge, and so on. So if I look at the layer charges per unit cell, I have exactly the same situation as in that simple cartoon we did earlier. I have plus 1, minus 1, plus 1, minus 1, equally spaced. And we saw already that such a structure has a polarization that doesn't contain zero. Okay, so the polarization, yeah, if I work it out then for this unit cell, then I have a charge of plus 1 at position 0. I'm working out the polarization out of the plane in the Z direction. I have a charge of plus 1 at position 0. I have a charge of minus 1, so minus E at position A over 2, where A is the unit cell, and I divide by the volume to normalize. If I took the blue square as my unit cell, I have a charge of minus 1 at position 0, so that contributes 0. Then I have a charge at plus 1, plus E at plus A over 2, and I divide by volume to normalize, and so on. So I have this polarization lattice that contains the half polarization quantum but doesn't contain zero. Okay. As a result of this then, because my bismuth ferrite in its centrosymmetric phase doesn't have zero as an allowed value of its polarization, this means that there is a surface charge associated with the polarization even in the centrosymmetric paraelectric phase. And you can see that also just kind of, maybe it's even more conceptual to think of it in this cartoon way. This layer which contains bismuth and oxygen is a positively charged layer. And so if I put a surface above that, I'm going to have a positive surface charge. This has nothing to do with any ferroelectric polarization. It's because of the internal layers of the material. Likewise, if I make the surface just above the FeO2 layer, I'm going to have a negative surface charge associated with putting the surface just there. And if I work out
the values of these surface charges in the ferroelectric units, what I find is that the surface charge associated with the bismuth oxygen surface is plus 50 microcoulombs per square centimeter, and the surface charge associated with the FeO2 surface is minus 50 microcoulombs per square centimeter. That's if I convert 1 electron per unit cell into ferroelectric units. And if you remember back to when we first looked at the polarization in bismuth ferrite, the spontaneous polarization in this 001 direction, the polarization that comes from the ferroelectricity when the bismuth ions displace relative to the rest of the unit cell, that also had the value of 50 microcoulombs per square centimeter, right? I want to emphasize this is completely coincidence. Bismuth ferrite is the only material I know where this happens. It's completely an accident, but it's going to lead us to some very interesting, I don't know whether to call it physics or chemistry, very interesting kind of physical chemistry as an outcome. So this, again, just to recap, this surface charge is coming just from the way that the atoms are layered. It's there in the centrosymmetric phase. It's nothing to do with the ferroelectricity. But then we have, in addition to that, a surface charge that comes from the ferroelectricity. Of course, in practice, they're both there, but we can, as a thought experiment, decompose them into these two contributions. Okay, so here's another cartoon. Here's my slab of bismuth ferrite. I've put an FeO2 minus surface at the top, and so I have a surface charge from the charged layers of minus 50 microcoulombs per square centimeter. I put a bismuth oxygen layer at the bottom, so I have a surface charge coming from this charged layer of plus 50 microcoulombs per square centimeter. Then in addition, in ferroelectric bismuth ferrite, in its polar ferroelectric state, I have a spontaneous polarization in addition to this, whose size is 50 microcoulombs per square centimeter. So you can immediately see then, depending on how the polarization is oriented relative to these surfaces, I can end up with a net surface charge that's either very large or cancels out to zero, right? So I have two combinations of polarization orientation and surface termination for which the surface charge from the spontaneous polarization exactly compensates the surface charge from the charged layers, from this half quantum of polarization. So if, for example, if I keep the same orientation of the bismuth ferrite, I have the FeO2 minus surface at the top and the BiO plus surface at the bottom, and I polarize it in the up direction. If I just leave the film sitting there, it will do this spontaneously. Then the surface charge from the polarization exactly cancels the surface charge from the layer, and I get a net surface of zero. And so this is where we find happiness in our electronic structure calculations. This is a really happy electrostatically completely content surface, right? There's no net surface charge, there's no diverging electrostatic potential. This, I can make a very, very thin film of bismuth ferrite, provided I choose this combination of surfaces and this orientation of polarization, and it's electrostatically stable. So this is completely remarkable. I mean, I think this has not been, it's very, very difficult to make a thin film of a ferroelectric and not have it want to explode. And in bismuth ferrite, it happens spontaneously because of this unusual cancellation. We should have realized this in prehistory when we first made this calculation, and I pointed this out to you earlier, that the total polarization, of course, normally when one calculates the polarization of a ferroelectric, one's only interested in the spontaneous ferroelectric polarization. And this was indeed what we were interested in at the time. But the total polarization can actually be zero, because the total polarization in this calculation, one has, of course, all the ions there. So the system knows about the internal charged layers. And bismuth ferrite in its bulk ferroelectric state can have a total polarization. One of the allowed values is actually zero. And this manifests in these happy surfaces. The converse, of course, is if you try to switch the orientation of the polarization of bismuth ferrite, it's even more unhappy than in a conventional ferroelectric, because you have the surface charge from the polarization adding to the surface charge from the charged layers, and it's doubly unhappy as it would be otherwise. This shows up in an electronic structure calculation. This is a calculation of the density of states as a function of energy. The Fermi energy is shown at zero, so this is the valence band and this is the conduction band. layer by layer through these slabs. And actually, let me start on the right-hand side. This is what a ferroelectric usually looks like, a thin film of a ferroelectric. You see there's a strong internal electric field, which causes the bands to bend. You can also see that the top of the valence band starts to overlap the Fermi energy at the top and the bottom of the, the top of the valence band and the bottom of the conduction band. This is making holes up here to try to compensate the negative charge and making electrons down here to try to compensate the positive charge. So this is a typical ferroelectric slab with the net polarization. In the happy configuration, there's no internal electric field because there's no surface charge. Okay, so these results I'm showing you now, and then the next couple of slides, I'm going to stop after a couple of slides, so don't worry if you're getting tired. But a result of a really lovely collaboration over the last couple of years, together with Chiara Gattinoni, who was a Marie Curie postdoctoral fellow in my group and is about to start her independent assistant professorship at the University of London. Marta Rossel, whose beautiful electron microscopy data I showed you earlier, who's now a microscopist at EMPA, the Swiss National Materials Lab. And Ipak Efe, who was actually a master's student in my group, who's now a PhD student actually growing thin films. She moved over to the dark side and decided to make samples. And these two papers came out just in the last months. One discusses a lot of the kind of technical interplay between this layer polarization and spontaneous polarization, if you're interested in the technical side. What I'm going to show you next is an application of this, of how these happy ferroelectric surfaces can be helpful in water dissociation, so generation of hydrogen for fuel cell and energy applications, and also water remediation, so for cleaning up water. So back to the saving the world question. Okay, so water splitting. So remember, we have two kinds of surfaces now. We have happy surfaces which are charge neutral, and unhappy surfaces which are extremely highly charged. And what we found, again, with our electronic structure calculations, is that on the happy surfaces, water molecules like to adsorb. They adsorb stably onto the happy surfaces, which is what you would expect, right? If you have a neutral surface, you're likely to be able to adsorb a neutral molecule. On the unhappy surfaces, we still have adsorption. There's still a negative adsorption energy, but this time it's for the dissociated ions of water. And of course, the OH minus ions adsorb, oh, I've turned this around, I'm sorry, adsorb on the positive charge surface, which is the bismuth. I had that on the bottom before, I apologize for that. And the H plus ions adsorb on the negatively charged FeO2 surface. So you could then envisage a cycle for effectively water splitting, in which when the bismuth ferrite slab is happy, water molecules adsorb on the surfaces. You switch it, for example, with an electric field, the water dissociates into the ions, and the positive ions stay on the negative surface, the negative ions leave, and the positive ions leave the positive surface and keep the negative ions. So we have a very effective way then of splitting the water into its constituent ions. Then you let the film relax back. The ions, the charged ions, are released, they're spat off the surface, it no longer wants them, and molecules are reabsorbed. So one has this nice cycle for water splitting. I want to show you some, I don't have the data to show you for this yet. I can tell you it's been done, but it's not yet published by our experimental colleagues. But I want to show you something related, which rather than water splitting, where the goal is to generate hydrogen, the goal was water remediation. And so this is the work of Salvador Pane, who's in the mechanical engineering department at the ETH. And Salvador took these very nasty toxic dye molecules. This is a vial containing, it's a cartoon of the molecule, of course, a molecule called rhodamine B, which is what's used to dye your genes and ends up, of course, in the water supply and wherever your genes are dyed. And he mixed this solution with bismuth ferrite. You can see not beautiful, pristine, thin films of bismuth ferrite, just bismuth ferrite nanoparticle crystallites, or micron size, I think, crystallites. And when he did that, he found that the bismuth ferrite broke down this nasty molecule into its constituents, into small molecules like methane and carbon dioxide and water, which are not toxic. And we think that the mechanism is very similar for the water remediation, as I showed you for the water splitting. What was nice, I'm not sure that it's useful particularly, but I think is rather cute, is that this process can be strongly accelerated using magnetic fields because of the multiferroic properties of bismuth ferrite. And so this was also a kind of nice feature. It's maybe not particularly useful, but it was kind of fun. Okay, I'm going to just quickly skip to the end because I had another example in case I had time, but I don't. So let me skip to the end because I have some homework for you. I'm giving you a long deadline. I tried to work out roughly your guys' age, so when you're likely to retire. So you have till summer 2065. So in your long and exciting careers, your job now is to pick one of these sustainable development goals, or more than one, if you like, and use the skills that you've been learning during the school and during the rest of your training, your electronic structure theory methods, and think about how what you're doing can contribute to reaching these goals and saving the world. So I showed you some examples of how our electronic structure calculations are helping with water issues and also with energy and climate action. I skipped over device physics. And yeah, so pick your own and go off and find your goal that you'd like to work towards. So that's the end of my talk. I'm very happy to take any questions, and very best wishes to all of you for your ongoing research successes, and particularly making nice electronic structure calculations with quantum espresso.
Thank you very much, Nicola, for this beautiful introduction and overview of the theory of modern theory of polarization, and these nice examples. And now we can all contribute to save the world just by sitting in front of our computer. I don't see any question for the time being. Alessandro, is there any question on YouTube? Please post it. Maybe I can start myself with a question. This actually has to do with temperature. Temperature effects can be relevant in some of these materials. I mean, I was wondering whether there is any theoretical approach. What would be the standard theoretical approach methodology to include also the temperature variable in these calculations?
Yeah, so basically by making effective Hamiltonians. So one can make an effective Hamiltonian and extract all of the parameters from density functional calculations, and then solves a model. I mean, in principle, I guess one could do, ab initio molecular dynamics and of a ferroelectric phase transition. I think it would be really challenging. But yeah, usually by if either some kind of lattice Bannier function type model are very popular, or of course Landau theory and extracting the Landau parameters from effective Hamiltonian from density function calculations. These are quite high. So bismuth, the example I showed you, the bismuth ferrite, the Curie temperature is really high actually. So even at room temperature, the polarization is not very different from 0 Kelvin. So it's yeah, but of course it's very relevant if you're interested in lower temperature materials, where the Curie temperature is a much lower temperature for sure. Yeah. Okay. Did you guys learn about ab initio MD this week? Did you do that in the school?
I think we did. There was one session on ab initio MD. Yes.
Okay.
We have a question from Ludovica. Are you? Yeah, you're unmuted now. Go ahead.
Yes. Thank you. Can you hear me?
I can. Yes.
Thank you, Professor, for this interesting talk. And I want to ask you a question about this particular phase, anti-ferroelectric phase. You showed us. I was wondering if I get the question is that this layer is naturally grown in this particular configuration. It's right.
Yes.
Okay. So my question is if some others' behavior can be tuned discovering other interesting phases with some external tuning of this phase, for example, strain or other type of growing of this structure for the devices?
Yeah, so that's a very good question. And so and one of the really appealing aspects of thin film growth is that one, of course, can grow the material on a substrate that has a slightly different lattice constant and strain the material, actually quite a lot, up to a few percent. And this has been done with bismuth ferrite. And so it's known, the phase diagram as a function of strain is known. And other things happen that are also very interesting, actually. So for example, if you compress it a lot, you end up with a giant polarization out of the phase. You get out of the plane, you get a new phase, which has a different symmetry and a giant out-of-plane polarization. This particular phase, the one that we looked at, let me pull it up again. This one is not very strain dependent. So the experiment has not been done, but this has only been grown on lanthanum ferrite. Has a rather similar lattice constant and a couple of other materials that have rather similar lattice constants. But computationally, Bastien actually looked at the strain dependence, and he found that actually over a reasonable range of strain, it doesn't change its relative energy a lot. So I think with this particular phase, actually we don't really want to modify it anymore. We're kind of quite excited to have it as it is, and it's fairly robust to moderate changes of strain. But that's absolutely a very good point. And in, I don't have a picture here. Bastien made a phase diagram of strain, electrostatics, and saw how if you modified one or the other, you could get into different regions of the phase space. Yeah, very good question.
Okay, thank you.
So now the ice is broken. There are several questions coming. I guess, Purinut, are you unmuted now? Can you ask a question?
Yes. Then it was said that the polarization of the solids has multi-value when we calculate it. So I can picture that. What is the meaning, physical meanings of the multi-value of the polarization? When perform the experiment, will it measure in many value, or anything I can picture it? Thank you.
I'm not sure I could hear you very well. Was the question, what is the meaning of the multi-value?
Yeah, what is the physical meaning of the multi-value?
Oh, yeah, that's a good question. So I can tell you how I think of it, and without a kind of whoops, I forgot to share my screen. Without a I'm not sure how rigorous this is, but this is the picture I have in my head. So here, are you seeing my my periodic solid again? Okay, let's imagine, so here's my periodic solid. Let's imagine I take an electron, say off of this anion, and I move it by 1 unit cell, right? So I do a thought experiment. I pick an electron off an anion, and I move it to the anion in the next unit cell. When I do that, it's a periodic solid, so every anion moves, sends an electron 1 unit cell to the right. So at the end, nothing has changed, right? My physical system is exactly the same. But when I take a charge and displace it by a distance r, my polarization has changed by the charge times the distance I've moved it, divided by the volume. And so that's how I think of the physical meaning, is that I can always change the polarization by any amount, by any integer, times the charge times the lattice vector divided by the volume. And that doesn't change the physical system. Does that, I don't know if that helps, but that's for me how I kind of reconcile this strangeness with kind of technically.
Okay, we have another question. Christian, you're unmuted now.
Yes, thank you, boss. I want to first thank you, the ICP member and all the organizers and the lecturers. My question is to know how the solvation effect is done in quantum espresso. Is it implicit or explicit? And for the molecular absorption of ferrite, with water? How is it done?
So yeah, I don't think we did these either in Quantum Espresso. They were also done with FAST. I have to confess, I'm really sorry, but we are doing some calculations at the moment with Quantum Espresso. So the water adsorption was done with, I don't remember the exact acronym of the functional, but one of the functionals that describes very nicely water. But you can look it up. It's detailed in the paper. But this is a very good point. For water, you have to be very careful to have a suitable functional that's appropriately describing the hydrogen bonding and so on. There are now many nice modern functionals that do this, and I'm sure many of these are also available in Quantum Espresso. And the kind of practicalities of the calculation, it was a very large supercell, so we could make a slab of bismuth ferrite. We had to force the polarization when we wanted it to be in the unhappy orientation. We had to kind of basically lock the polarization in the unhappy orientation, otherwise it always wanted to switch back the other way, so that was a little bit complicated. Yeah, and then of course make sure to have a functional that's able to appropriately describe both the water and the ferroelectricity of bismuth ferrite. And I apologize, I don't remember the name of the functional that's used.
Okay, we have a question from the YouTube chat about the choice of pseudopotentials, whether there is anything that you can recommend in terms of choice of pseudopotentials, ultrasoft, PAW, for calculation of polarization in general.
So I think that, hopefully your choice of pseudopotential shouldn't matter, right? I mean, it should always give you the same answer. Of course, every pseudopotential you take, one has to test in the situation that you're using it in. I think what's maybe more delicate is the choice of exchange correlation functional. And so this has to be carefully tested that it's appropriately describing the ferroelectric polarization. Because if you think about this polarization when the anions and cations move off center, this is quite a delicate description of the bonding process between the transition metal and the oxygen, and so that also has to be chosen quite carefully. But I don't have any, hopefully all pseudopotentials should give really the same answer. And these days, you guys are kind of fortunate these days because you have good libraries and they're often very well tested. So we had to make our own in the olden days, and then it was then I guess you really knew what you were getting. So. Different.
Okay, we have a very last question for one of the students, Stefano Baroni. Who is this? Stefano, you can unmute yourself.
Well, I said, Sandro, I will rather give up my question and leave more room to participants.
Yeah, I think we're essentially done with the questions. There are no further questions from the participants. So I think if you want to ask a question, yes, a couple of minutes.
Let me just ask the last one. So Nicola, first of all, thank you for this spectacular lecture. I think we all enjoyed very much, and me particularly. So the difference between a happy and an unhappy surface, if I understand correctly, is the volume contribution to the total energy of the system that takes a term that is the square of the electric field times the volume, right? So if you have a macroscopic field in your sample, you have an electrostatic energy that is E squared times the volume, right?
Yeah.
And in order to neutralize, in order to make the surface happy, it would be enough to neutralize the surface with some charge rearrangement, right?
So in the happy,
which means
sorry, go ahead. Yeah.
No.
So in the
happy
surface, if you like, there is no surface charge because the ferroelectric polarization is neutralizing the surface charge from the layers. Or if you like, in the happy situation, the polarization is actually zero because the spontaneous polarization cancels the layer polarization. So there's nothing to neutralize.
We probably have a different conception of happiness. I thought the opposite. I thought that when you have take a polar system, take a system, a ionic system, and if you have a polar termination of your ionic system, you could have in principle a surface charge that would give rise to a bulk energy proportional to the square of the internal field, right?
Exactly. Yeah. And in the happy
situation, this is usually compensated by a local rearrangement, the surface atoms and surface charges, that costs an energy proportional to the surface that compensates a bulk energy. So eventually, it is always favorable to rearrange the charge at the surface, paying a small price to make a big gain in the volume.
Yeah, exactly. Yeah. And in the happy situation, you don't have to do that. You don't have to pay that price, because the surface charge that's coming from those ionic layers, basically the polar surface, is compensated by the polarization from the ferroelectric.
Yes.
So that's why it's happy. Whereas in the unhappy surface, you still have to, in practice, of course, you have to do something like you reconstruct the circuit, add extra surface charge, have a metallic electrode to screen it, adsorb positively charged hydrogen.
Okay. But so the mechanism is similar to what I was describing, but I was describing what would happen starting from a non-polar system, ionic, for instance, a centrosymmetric ionic system, and you were describing exactly the same mechanism for a system that is intrinsically polarized, because it is ferroelectric or whatever, right?
Yeah.
But the difference between happiness and unhappiness is just the local rearrangement at the surface of atoms and charges at the surface, right? You can always pass from happiness to unhappiness just by swapping a few atoms or by adding some charge at the surface.
No, because in the unhappy, well, yeah, if you add, well, no, I don't think so, because if internally let's say you keep your surface planes, the same surface planes, say FeO2 at the top and BiO at the bottom. To go from happy to unhappy, you really reverse the polarization. So it's like in one case, the bismuths have all moved up. In the other case, the bismuths have all moved down relative to the other layers in the unit cell. So it's the polarization is
from the point of view of bulk symmetry polarization up and polarization down are two different realizations of the same broken symmetry. They have the same bulk energy.
But they're the same bulk energy. Okay, so they're the same bulk energy, but you've changed their orientation relative to the surface. So for sure, you could pass from happy to unhappy by putting half a unit cell on the surface. So if I'm in, say, up and FeO2 minus and I'm happy, if I put a layer of bismuth oxide on the top, then I become unhappy. Exactly. Yeah, exactly. Okay, that's what you mean.
Okay,
yeah.
But in that sense, you pay. So the difference from happiness to unhappiness costs a surface price, not a bulk price, because you do something at the surface and you pay something per unit surface. But doing something on the surface, you pay a surface price, but then you gain or lose a bulk energy. Because you switch an electric field on and off.
Right. Yeah. Yeah.
Stefano, Nicola, can I suggest that perhaps you continue this discussion
okay.
offline?
Yeah,
because
maybe
it's getting,
people want to go and have that weekend
I
with
knew
students.
that I had better not
I want to make sure we have a happy ending to this. To this. So
okay.
We discuss later. So.
If you don't mind, Nicola, I will ask you the question in person the first time we meet.
Over a good espresso. Yeah.
Very good.
Yeah.
Very good. Classical espresso,
classical
not
one,
quantum.
yes.
Classical one.
Classical espresso.
Nicola,
thank you very much.
Thank
You're
you
welcome.
very much.
Thank
Nicola,
you all.
there are dozens of thank you messages in the chat that we will send.
Okay, I'll sit and read them
afterwards.
while Elisa is speaking.
Yeah, so thank you very much again, and we'll close.